We're going to talk about a little bit of the brief history of deep learning and why it seems to be so popular and doing so well right now in particular. Also, while we're doing announcements, I have the chestiest of chesty coughs, so I'm going to try really hard not to cough up a lung in front of you tonight. But if I do, you can all go home early, or rather go to the pub early. So, let's do this. As Joe said, I'm a PhD student at the moment at the University of Dundee. I'm doing a PhD applying deep learning techniques to biomedical data. Particularly, this works with protein science. So looking at the proteins in the human body and how they react to disease or to drugs. Interestingly, that data is very, very high dimensional. So hopefully we'll be able to do some interesting work with deep learning on that. Prior to that, I did a fabulous master's in data science at the University of Dundee. This is not sponsored, but it is a very good course, you know, in case you're interested. Prior to that, I did about 4 years in industry. And before that, did a master's degree. I actually left my master's degree thinking I wouldn't go back into the technical industry. You know, F that. But I'm not sure how I managed back into, not industry, but technical nonetheless. However, I get paid to learn, which I think is pretty cool. So, quickly, if you weren't in my talk earlier, I'm going to quickly define some terms for the context of this talk. So, deep learning, machine learning, AI, everyone has different definitions, and I like to just get things straight before I talk about them. So, for me, deep learning, what we're going to be talking about the history of today, is the field of complex multi-layer neural nets and how they've become to be good at what they do or good at what we've asked them to do. The wider field, I would say machine learning is more about shallower learning, those kind of classic methods we've had to work for decades, whereas deep learning seems to have only really worked recently, which is a question we'll sort of explore in this as well. For me, those fit into the wider field of AI, and people debate this a lot, actually, these definitions, because I think everyone's is different. However, for the purposes of this lecture, we're going to focus right in on deep learning in particular. Also, another caveat, I feel like this has been announcement after announcement after announcement, but the caveat is whenever you do a brief history of anything, there are always people left out. Isaac Newton is attributed to this quote of, you know, standing on the shoulders of giants. And the collaborative nature of research is that we build on what has come before. And so we can say that so-and-so invented something, so-and-so invented something else, but in reality, nothing is created in a vacuum. And so a lot of the people that I might point out today or highlight today worked with potentially teams of their own, or were part of a team, or built on work that their team had done in a previous day. So, if anyone is interested, I would encourage you to read around on the subject. And hopefully I don't offend anyone by leaving them out. Not that they're going to be watching this or anything, but, you know, just in case. So, what we're going to go through in the next about half an hour-ish is talk about some landmark events in the sort of timeline of deep learning, networks of note that I think people think have contributed to the growth of the field. We're going to look at what type of growth it's been. People talk about it being exponential growth, but is that really what's happening? And then briefly, let's touch on the issues. People like to obviously drop the buzzwords AI or deep learning or anything related into things today, sometimes to ride on the coattails, but I think it's worth considering what the issues may be with that, the knock-on effect that could have to the industry. So, A brief timeline. 1943, I think a lot of people know this as this is the original conception of neural networks in a mathematical sense. How could we translate the way our neurons and synapses work in a digital way? The perceptron in there by Rosenblatt being our first real kind of neural network. The perceptron is technically a single layer network, and it was very good at certain things, but not others. So there was a bit of a landmark paper published in 1969, which everybody kind of blames for the first AI winter. Essentially, in this paper, they pointed out the shortcomings of perceptrons, and that actually to get past those shortcomings, we would need multi-layer networks, which we couldn't do feasibly at the time. So this is kind of when people tend to agree this is the first sort of AI winter, as it were. And then it isn't really until the late 80s that we see interesting things happen again. So very famously in 86, the joy of backpropagation is popularized. And I say popularized because, you know, like when you stand on the shoulders of giants, these things existed in slightly different forms before. And so it was kind of through the early to mid-80s that we came up with backpropagation. But actually, this is one of the papers that really projected it out into the community. And actually, it's a really interesting thing to think about because you can be the person who comes up with something and releases it, but it might not necessarily gain any traction. So in the research industry, I think we call that impact. So beyond 1986, we have a couple landmark networks. We have the first recurrent neural network, or at least the first version of recurrency used in networks. You've just reminded me that my phone's not on silent. Oh dear. So, first version of recurrency used in neural networks. This is used, is very popular today. Anything that's sequential, particularly in time. So, words, sentences, speech, things like that. And we also had one of the first implementations of convolutions and CNNs, so convolutional neural networks, which they just kind of own the game in terms of image recognition these days. And actually, convolutions are very, very powerful in neural networks in general, even beyond image recognition. So people sort of describe the 90s and maybe the early noughties as a second AI winter. And it depends how you want to look at it. But realistically, I've read a few interviews with some kind of the different big players in the industry who were in it from the 80s onwards, who say that actually it was really difficult to get scientific funding, particularly in the 90s, if you wanted to publish something that contained work on a neural network, and particularly the word neural network, or the phrase, I should say, neural network, which is quite interesting. And Geoffrey Hinton, who we'll talk a bit about later, one of the forefathers of deep learning, describes getting this funding grant accepted in 2004, which made a really big difference to his research team. They were one of the strongest research teams kind of in the history of deep learning, to be honest. And so then regaining substantial funding, he says, made a really big difference to his team. And actually his team went on to have a really big impact in the field. So 2004, money starts to trickle back into the industry, or technically starts to flood back into the industry. And we also have another breakthrough in 2006 when we get a bit better at deep training strategies. So the joy of backpropagation can only go so far. Actually, we had to deal with some issues surrounding its implementation. And so we get a bit better at that in the mid-2000s. Now, we have to kind of zoom in a little bit so it won't hurt your eyes. But we're now in 2010, and to be fair, I would say a lot of landmark things, I think, have happened. So, GPUs, I guess most people know what a GPU is, but in terms of running a deep learning network on a CPU, the acceleration in training time on a GPU made a substantial difference. And if you think about it, it's not about just training an individual model, but actually, if you're developing an algorithm that will form the basis of a model, you're still going to train and test and tweak that algorithm, not to create a model, but as the algorithm itself that creates the model. So any of your optimization strategies and things, you can look at them faster, assess them faster, find out what works faster. And so everything accelerates, not just the training of one single network. Not long afterwards, we discovered the joy of nonlinearity, which is basically the power behind multi-layer networks, in my opinion. You can have multi-layer networks until the cows come home with linear activation functions inside, but actually that doesn't have the same representation power as non-linear activation functions. So I think a lot of people are familiar with the famous ReLU, and actually it's astonishing what a small function did to the capabilities of neural networks. And we also discovered that we can initialize the weights in a network a bit better. So in reality, that translates as we know where to start a bit better, and we know how to make it a bit better, or rather, a lot better. And we know how to do it a lot faster. So 2012, I think, was a real turning point in the industry because a lot was now starting to happen. More research was done, and that when more research is published, people tend to get more funding because it's an interesting area, and so it snowballs. But actually, I think one of the turning points in particular is there was a paper published on speech recognition by a collaboration of 4 groups. The University of Toronto, so we've spoken about Geoffrey Hinton before, that was his research group. These people called Microsoft, Google, and IBM, don't know who they are, together released a paper showing how well their deep network performed on speech recognition. And it was one of these papers that really inspired a lot of people to think differently about deep learning, or think differently about neural networks in general, because anyone who'd maybe seen them peak in the 80s and saw them die away and thought they really weren't worth anything, I guess they started to see papers like this and go, oh, actually, maybe things are starting to change. Another one was now known as AlexNet. It's a really common image recognition network. And that was published, again, supervised by Geoffrey Hinton. This guy gets everywhere. Another major paper that showed the kind of improvement that deep learning had now as of the mid-2012s, and Dropout. So Dropout is really powerful in terms of regulating big networks. So obviously, the bigger and bigger the network you create, you can get into some trouble with the size of that, basically, and how many times you are convoluting or processing the data. And astonishingly, Dropout means that at certain stages, you just throw bits of it away. Essentially, that's a very kind of basic description. Don't quote me on that. But essentially, we discovered the power of dropping out partway through bits and bobs, partway through networks. Now, dropout is implemented in so many architectures, so many deep architectures. And 2012 was, or I think, when things really started to turn and really started to upswing. And when it comes to networks of note, another one I would say is GANs, so generative adversarial networks. Has anyone not heard of GANs? Let's see. Oh, wait, there's one hand. Okay, a couple more. Well done. If you haven't heard of GANs, have you heard of deepfakes? Yeah, no? Oh, you might want to Google that, actually. So, generative adversarial networks, only been invented in 2014, but actually they've made some of the biggest strides since then, and obviously have been rather highly reported in the media for what they have, what they've been creating, whether that's generating fake faces, generating fake videos. They generate things, for want of a better word. And I think even though it's a very, very new architecture, it's had a real impact in terms of the popularization of deep learning. Maybe not just the popularization, but the sensationalization, which is maybe a good thing and a bad thing. But I think there's pros and cons with any kind of media coverage, isn't there? So, beyond that, a couple of years afterwards, we have the TPU, so the Tensor Processing Unit. So hopefully, or ideally, meant to accelerate stronger than a GPU. I don't know how much these have been widely adopted. Obviously, I'm in the academic industry. They've not quite hit us yet, although no, I don't think they've quite hit us yet, in my experience, where I do my PhD. However, again, it's another acceleration framework that I think will change the game as time goes on. I think in particular, people have started to realize that actually things like custom chips are achievable and actually might be the way to go to tailor these types of things. Just my opinion. So, on from generative adversarial networks is the rise of deepfakes. And I guess you might be surprised to hear deepfakes spoken about in terms of a history of deep learning, because they're very, very recent, but actually I think they've had a really strong impact. Potentially a bigger impact on the wider field of artificial intelligence, because that's how you see people describe them, whether they are artificially intelligent or not is for us to debate in the pub. However, I do think that, again, much like I was saying earlier about GANs, I really think that the media coverage of this has really popularized it, as well as obviously things like data science being described as like the sexiest job of the 21st century. I had to think what century we were in there. 21st, right? 21st century. Again, the popularization in this of the media means that it's more accessible to a wider audience to, well, sort of see what's going on or become interested in what's going on. I think that inspires new researchers sometimes, or people who want to get into the industry. Part of that, I think, is accessibility. So obviously, there's lots of different deep learning frameworks. Tensorflow, in my experience, is one of the most widely adopted. There's a bit of a half and half between academia and the commercial world. But in terms of the commercial world, I would say, and the average person, I think TensorFlow is a lot more adopted. And so why I think this is important is that Keras was such an accessible way to use TensorFlow and to get deep learning up and running. I really think it's done a lot to democratize the kind of avenue into deep learning for people to get in and try it and see what it can do, see if it's interesting to them rather than a person new to the industry thinking they have to go away and get a whole degree, 4-year degree in this before they start doing it. I think people can get up and running really fast, and I do think that's contributed a lot. Finally, the point I want to talk about is the Turing Award. So I think whether you believe in the recent success or popularity of deep learning or think it's just old things rehashed, the Turing Award was issued to 3 of the main researchers that have been going at it since, I was going to say since the 80s, but actually I don't want to offend any of them if that's not true. For a very long time. For a very long time. And these guys are Benyu, Hinton, and Jan LeCun. Hinton we've heard of before, funnily enough. A lot of the papers that cross over with him are done by Benyu or LeCun, and we can actually look at what they've done. I think this is a really interesting look, actually, at not only have they been recognized for what they've done, so deep neural networks as a critical component of computing. You can actually see these are citation counts. So whenever a researcher releases a new paper and they cite work by previous researchers standing on shoulders of giants, they're citing the giants. Google Scholar indexes that, and you can get reports like this that show that actually the citation count of these researchers and their papers has been rapidly growing. This graph starts here at 2012 and 2019. Remember, we're not quite through 2019 just yet. So I think that final bar has got a way to go. And so I think it's quite telling. But of course, that doesn't cover how many papers have been published. But we can look at that, actually. And I'm afraid that legend's a bit small, I'm sorry. But this is from the 50s up to today, a count of research documents. So this could be papers, reports, etc., that are indexed on a fabulous website called Web of Science. This is something that I'm very privileged to have access to as an academic, and I can go on and search for papers and look by keyword and by area and all sorts of things. So I went on and I looked at papers that quote deep learning. So that's the blue line, which is actually the bottom one there that swoops up. Machine learning, which is the second red one above it. And anything that mentions the phrase neural network or neural networks, which is the green line that shows the highest count. So, interestingly, neural networks in the green at the top line has the most counts, but has gone through some interesting dips and troughs. But we are a bit more interested in the growth. So if you excuse the change of charts, instead of looking at purely the number of documents that are published on these, with these phrases, research documents, excuse me, we can look at the year-on-year relative change. So has it gone from 100 to 200? Or has it gone from 100 to 500? And so actually, most of these points are gathered around number 1. And in relative change, that basically means not a lot of change. But interestingly, with deep learning, which is the blue dots, it's a lot more scattered until about, 2008, 2010, 2012, when actually the relative growth really moves away from the growth of that of neural networks and machine learning alone. So, I mean, these searches, I should say, aren't exclusive. So a paper that mentions deep learning might also mention neural networks. But actually, the overlap shouldn't be so much that this is not relevant. And so it is interesting to see that whilst studies using the words neural network have the largest corpus of documents, having the largest bubble size there, actually deep learning since 2012, 2010 has been outstripping in terms of growth. And it'll be interesting to see how that plateaus or not over the next few years. So, why? We've looked a little bit at the history and about why certain events, landmark events that might have changed their perception or the ability of funding or the representation power of neural networks. And I think actually this is a really useful little graph in terms of describing the representation power of a network. So you can think of that in terms of how difficult a job can it do, how difficult of a thing or how complex of a thing can it describe, can it represent. And actually, this is linearly related to computational complexity, which is where we would need more training time, better optimized algorithms, and all sorts of those things. So you can see there's an interesting relationship there. This is the first bubble on the left-hand side is the self-organizing map, which is a funky classic ML algorithm. And actually, that what have we got listed as 1980? And actually, each bubble, as it goes up in computational complexity and in representation power, we actually are progressing through the years as well, for the most part, which is kind of interesting. Another thing to think about is the availability of data. I mean, I think, obviously, everyone is in this room because of data. But this is, I find, a really useful graphic in terms of thinking about the power of shallow learning, or what you might call classic learning, versus deeper networks. This is from a really accessible book by Andrew Ng. Andrew Ng is another one of the kind of godfathers of deep learning. He wrote the very famous, I think it's an Intro to Machine Learning course on Coursera or something. A lot of people I know have come into contact with that. It's a very good course. However, he wrote a book very recently, which is more geared towards non-technical people, or non-technical readers, I should say. So if you are a manager of a team, or you just want to find out in a more businessy sense how this whole deep learning shenanigans relates to you, I quite like that book, actually. And in here, he describes the difference, really, between the performance we can get out of a network, shallow or deep, in comparison to the amount of data. And so we're talking about sample size here. So do you have 100 examples to train your model on? Do you have 1,000 examples? These days, that is probably a lower end, sample size. These days, a kind of large amount of data, you're talking gigabytes, terabytes. So, not only do we need computational complexity to have representation power, we need big data to drive the training. So, we've spoken about the reasons behind the potential growth or boom, I guess you could say, of deep learning. We've talked about the algorithm development, how we've gotten better at training strategies. We've gotten better understanding non-linearity. I don't know why that's so difficult for me to say. Non-linearity. We've gotten better at computing resources, CPUs, GPUs, TPUs. Goodness knows, what else is coming next. And we've spoken about the availability of big data. And so not only is that about the digitization of data, and so being in the internet age, we store almost everything. So now it's being stored. It's also about democratization. It's also about the fact that it's available to people. There are many great places online where you've been able to go for years to download larger, more interesting data sets. And again, for me, that's another point of accessibility. It democratizes this type of modeling to the every person rather than a researcher in a university group somewhere, up in a tall tower. We have also touched on the idea of research funding and the idea of money and the media and actually the impact that can have. It is really interesting, actually, the effect that the media can potentially have on research funding. I think that it's a tricky one because obviously as an academic, I have funding. I'm funded by the Medical Research Council, if anybody's interested. And I do think there is a link that we can't deny between the media and what's popular or sensational at the moment and things that funding bodies might hear about and might be interested in funding. I think it's certainly naive to assume otherwise. So, issues with this. As we can see, I think we are going through a period of rapid growth. However, I do think we need to consider the issues with that. And I think that we are beginning to address them now. I think they are beginning to reach the media now. So, lack of rigorous testing of models. For example, models doing things that we don't know they were going to do, but if we'd tested them thoroughly, maybe we would have found it, not sure. Examples of that might be, there's a couple of classic examples in image recognition where networks are telling the difference between dogs and wolves. There's lots of pictures of dogs in residential settings, and there's lots of pictures of wolves in snowy forestry settings. And actually, some work pointed out that the important part in the distinguishing in the network between the dog and the wolf was the snowy background rather than the differences in the two animals' appearance and shape. These type of model issues, model accidents, we don't really know, I guess, how common they are, and that is a problem. Another point that fits into that is regulation or accreditation of people who build models that go on to be decision makers, things that affect people. I think there's going to be a couple of really interesting talks and discussions on that, actually, at this conference, which I'm looking forward to. Overuse and overfitting. Sometimes you just don't need a giant network. You might want to use it because it's fun, but actually, the simpler, the better, really, because then you don't necessarily have to worry about your wolves in the snow. Inflated expectations is one that I did want to touch on. It sort of fits in, I guess, definitely fits into what I was saying about the media and the popularization, the sensationalization of artificial intelligence coming to kill us all, or deep learning, creating fake videos that's going to demolish politics as we know it. I think that can have a really interesting effect on, say, not only the research community, but anyone who works with machine learning or deep learning models, because I do think it does inflate expectations, and people expect not necessarily crazy results, but all these kind of extreme things that they hear about sensationalized in the media. And it can prime people for, inflated, unrealistic expectations. That can be hard to deal with, whether you're in industry or academia, I guess, because it might be your boss who's saying, oh, but well, why can't we make it awesome? So I saw someone nod there. So I guess the point I guess I would make about that is to consider it with a pinch of salt when it is overly hyped in particular articles. Not by the Register, of course. So we've been through the timeline from the 40s to now of what I think are important parts. And we've talked a bit about the rapid growth or the potentially exponential growth and what the issues can be with those. And so that leads us really to the end of the talk. So thank you very much for listening. And if anyone has any questions, I'd be happy to answer them now. Okay.